High above the Earth's surface lies a realm where the sky transitions into the blackness of space. This boundary, often invisible to the naked eye, marks the beginning of a vast and mysterious expanse that has fascinated humanity for centuries. This region, known as the thermosphere, is a rarefied layer of gas that forms the outer boundary of our atmosphere. It stretches from about 80 kilometers to 600 kilometers above the Earth, encompassing the area where auroras dance and meteors burn up. Though often overlooked, the thermosphere plays a crucial role in protecting life on Earth and enabling our technological advancements in space. It is here that the International Space Station orbits and where many satellites operate, providing us with vital communication and navigation services. It acts as a shield against harmful radiation from the sun, absorbing and reflecting ultraviolet and X-ray radiation that would otherwise be detrimental to life on our planet. It also provides the drag that helps satellites maintain their orbits, ensuring that they do not drift away into the void of space or fall back to Earth prematurely. However, this delicate balance is now under threat. Human activities and natural phenomena are altering the dynamics of this crucial layer. The thermosphere is not as static as it seems. It is a dynamic environment, constantly changing in response to various external and internal factors. Its density and temperature fluctuate in response to solar activity and other factors such as geomagnetic storms and cosmic rays. One such factor, previously underestimated, is the increasing concentration of greenhouse gases in Earth's atmosphere. These gases are not only warming the lower atmosphere, but also having unexpected effects on the upper layers. While often associated with global warming, these gases are having a paradoxical effect on the thermosphere, causing it to cool and contract. This cooling can lead to a decrease in atmospheric drag, affecting satellite orbits and increasing the risk of space debris collisions. This seemingly distant phenomenon has profound implications for the future of space exploration and the sustainability of Earth's orbital environment. As we continue to explore and utilize space, understanding and preserving the fragile boundary of the thermosphere becomes ever more critical. Carbon dioxide, a byproduct of human activities like burning fossil fuels, has become a major driver of climate change. This invisible gas, though naturally occurring, has seen its levels skyrocket due to industrial activities, deforestation, and the burning of coal, oil, and gas. Its impact, however, extends far beyond the Earth's surface. The consequences of increased CO2 are felt in every corner of our planet, from the deepest oceans to the highest mountains. As CO2 levels rise in the lower atmosphere, they trap heat that would otherwise escape into space. This trapped heat leads to more frequent and intense heat waves, altering weather patterns and affecting ecosystems. This process, known as the greenhouse effect, is responsible for the observed warming trend on Earth. The greenhouse effect is a natural phenomenon, but human activities have amplified it to dangerous levels. However, the story doesn't end there. The effects of CO2 are complex and multifaceted, influencing not just the climate, but also the very structure of our atmosphere. When CO2 molecules absorb this trapped heat, they radiate some of it back towards Earth's surface, contributing to further warming. This feedback loop exacerbates the warming effect, making it a critical issue to address. However, they also radiate some of it upwards into the thermosphere. This dual action of CO2 molecules creates a complex dynamic in our atmosphere. This upward radiation of heat from CO2 molecules has a cooling effect on the thermosphere. The thermosphere, which is the outermost layer of Earth's atmosphere, responds to these changes in intriguing ways. As the thermosphere cools, it loses kinetic energy, causing its gases to slow down and move closer together. This cooling effect is a lesser-known consequence of increased CO2 levels. This process leads to a decrease in the thermosphere's density and volume, effectively shrinking this vital layer of our atmosphere. Understanding these impacts is crucial for predicting future changes in our climate and atmosphere. The shrinking thermosphere might seem like a distant concern, but its consequences are far-reaching and potentially catastrophic. One of the most significant impacts is on the growing problem of space debris. Every satellite, spent rocket stage, and even tiny fragment of debris left in orbit poses a collision hazard to operational spacecraft. The thermosphere, in its natural state, acts as a natural cleansing mechanism. The drag it exerts on objects in low Earth orbit gradually slows them down, causing their orbits to decay. Eventually, they re-enter the atmosphere and burn up, preventing a runaway accumulation of debris. However, as the thermosphere shrinks and its density decreases, so does the drag it exerts on these objects. This reduced drag means that space debris will remain in orbit for much longer periods, increasing the likelihood of collisions. The implications of a more congested and hazardous orbital environment are particularly concerning given the increasing number of satellites being launched into low Earth orbit. Companies like SpaceX, with its ambitious Starlink constellation, are placing thousands of small satellites into orbit to provide global internet coverage. These mega-constellations, while promising in their technological aspirations, exacerbate the challenges posed by a shrinking thermosphere. Starlink satellites, designed for high-speed internet, are particularly vulnerable to collisions due to their low orbits and sheer number. As the thermosphere shrinks and space debris accumulates, the risk of collisions with these satellites increases dramatically. Even a small impact can have devastating consequences, potentially triggering a cascade of collisions that could render entire orbital planes unusable. This scenario, known as the Kessler syndrome, could cripple our space infrastructure and set back space exploration by decades. Section 5. The shrinking capacity of Earth's orbit. The shrinking thermosphere and the escalating problem of space debris are not just technological challenges. They represent a fundamental shift in our relationship with space. As the thermosphere contracts, it reduces the natural drag on space debris, allowing more of it to accumulate in orbit. As we continue to launch more objects into orbit, we are effectively reducing the carrying capacity of low Earth orbit. Each new satellite or piece of debris adds to the congestion, making it increasingly difficult to navigate and manage. This finite resource, once thought to be limitless, is now facing sustainability issues. The crowded orbits pose risks of collisions, which can create even more debris, leading to a cascading effect known as the Kessler syndrome. The concept of carrying capacity, often used in ecology to describe the number of organisms an environment can sustainably support, is now relevant to our use of space. Just as ecosystems can collapse when their carrying capacity is exceeded, so too can our orbital environment. The shrinking thermosphere, by reducing the natural removal of debris, is effectively decreasing the carrying capacity of low Earth orbit. This means that debris remains in orbit longer, increasing the likelihood of collisions. This means that we will need to develop more sustainable practices for space exploration to avoid creating an unmanageable debris problem that could jeopardize future missions and our access to space. Innovations in debris removal and collision avoidance will be crucial in maintaining the usability of our orbital environment. Section 6. Navigating the debris field. A technological challenge. Addressing the challenges posed by a shrinking thermosphere and an increasingly congested orbital environment requires a multifaceted approach that combines technological innovation with responsible space governance. On the technological front, there are ongoing efforts to develop more sophisticated collision avoidance systems. These systems use ground-based radar and optical telescopes to track objects in orbit and onboard sensors and propulsion systems to maneuver satellites out of harm's way. Artificial intelligence and machine learning are playing an increasingly important role in these systems, enabling them to process vast amounts of data and make real-time decisions to avoid collisions. While these technologies are promising, they are not a complete solution. Collision avoidance systems are reactive by nature, and their effectiveness depends on the accuracy of tracking data and the maneuverability of the spacecraft. Section 7. The imperative of debris reduction. In addition to collision avoidance, there is a growing need for active debris removal technologies. These technologies aim to capture and deorbit large pieces of debris, such as defunct satellites and spent rocket stages, to prevent them from colliding with operational spacecraft and creating more debris. Several concepts for active debris removal are being explored, including nets, harpoons, robotic arms, and even lasers to slow down debris and cause it to re-enter the atmosphere. However, these technologies are still in their early stages of development, and deploying them on a large scale presents significant technical and financial challenges. Section 8, a collective responsibility curbing greenhouse gases. While technological solutions are crucial for mitigating the immediate risks posed by space debris, addressing the root cause of the problem requires a global effort to reduce greenhouse gas emissions. The shrinking thermosphere is a stark reminder that our actions on Earth have consequences that extend far beyond our planet's surface. International cooperation is essential to implement policies that promote sustainable development, transition to cleaner energy sources, and reduce our reliance on fossil fuels. By addressing climate change, we can mitigate the long-term risks to our space environment and ensure that future generations can continue to explore and benefit from the wonders of the cosmos. Section 9, securing our future in space. The shrinking thermosphere serves as a potent symbol of the interconnectedness of Earth and space. It underscores the importance of responsible stewardship of our planet and its surrounding environment. As we venture further into space, it is imperative that we do so with a deep understanding of the consequences of our actions and a commitment to preserving the integrity of our celestial neighborhood. The future of space exploration depends on our ability to address the challenges posed by space debris and a changing space environment. By embracing innovation, fostering international collaboration, and prioritizing sustainability, we can ensure that the final frontier remains a realm of discovery and wonder for generations to come.